Well, it's a story of diffraction. So diffraction is, simply put, if you've got a sound source and it's existing on like a plane, as we see the front baffle here, the sound's going to leave the tweeter, and not only does it go forward, but it goes to the side. And the sound that goes to the side is going to reach an edge or anything that's in its way, and it's going to reflect off of that. So you'll get a reflection here, and a reflection here, a reflection here, it'll reflect off all of those things. Those reflections will sum together out in the listening space. So now you've got, you know, the sound coming from here, and I get sound coming from here, and sound coming from here. Tends to blur the imaging a little bit, or cause some frequency response anomalies, or things that we don't want, let's just say. So there are ways to mitigate that. The number one way to mitigate it is to reduce the abrupt change in going from this flat plane to nothingness over here for the most part. And that would mean rounding off the corners. Well, you're not going to have this speaker if you round off the corners anymore. It won't look like this. So the next thing we can do is to try to reduce the fact that if it's in the center, these two reflections will arrive at the same time. Well, if we offset it a little bit, it takes longer to get to this edge than it gets to this edge. So that's going to help us to reduce the problem with diffraction, and that's why the tweeter's offset. These cones and the cones that are in the BP line are mineral-filled polypropylene, which has a lot of the properties we look for in a cone, which is high internal damping, high speed of sound, stiffness, that sort of thing. Polypropylene's, you know, a good quality material for that. Linear response waveguide, what it does is it improves the off-axis performance of the driver by blocking some of the sound. So if we have to think now in terms of interference. So if you imagine that sound from this driver is coming from every point on this driver. If we sit out here in space, all of those points are all lining up at the same time. But now as we move in this plane, it's taking longer from sound radiated from here to get to that point than it is from this side. And you start to get this interference pattern, what we call comb filtering. So what's happening is this waveguide is affecting that path length, and it's actually blocking some of the stuff and some of the waves. And what it does is it ends up smoothing, giving you a little bit more off-axis dispersion than you would get otherwise. So we went with passive radiators on the Demand series. It's part of one of the things that Definitive Technology tends to use on a lot of its loudspeakers, and there's reasons for that. One is with a port, you get port noise, right? You get this rushing sound, kind of noisy sound. You don't get that with a passive radiator. It's not air anymore. It's an actual diaphragm moving back and forth. Another thing is that the passive radiator gives you a lot more options in terms of tuning the low end. With a port, you pretty much can change the frequency that it's radiating at, and that's it, right? With a passive radiator, we can change in multiple ways, so it gives us a ability to tune the low end better. The dual spider thing is to prevent rocking motion in the passive radiator. So if you think of it, well, we think of it in terms of moments. So if we've got the outer surround is out here, well, it's pretty flexible, so it can move like this. So we put a spider in the center, but if that's floppy enough, then it'll still allow it to go like this. But now if we've got two, now it's a lot harder for it to move side to side. So it makes the passive radiator more pistonic, we say.